Welcome back to Module 202C, Part 3. Now that we know why we have series RLC circuits and we know how to analyze those circuits, we're going to work on solving them. In this part, we're going to look at two different RLC circuits and go through them step by step to find the solutions. Our first circuit is a resistor, a coil, and a capacitor all in series. Just like we did with RL circuits and RC circuits, the first thing we want to do with any series circuit is start with our impedance triangles. We have our resistor, and our coil, and a capacitor. So on these three items, we're going to put in our known values. For our resistor, it's 6 ohms. For our coil, we have 3 ohms resistance. And when we convert the inductance, we'll have 47.9 ohms of inductive reactance. For a capacitor, we take our microfarads. We use our formula to get our XC of 14.3 ohms. In order to get our total circuits, we have to add up all of our horizontals and all of our verticals. So 6 plus 3 is equal to 9 ohms of total resistance on my circuit. For my total reactance, I have to take my inductive reactance and subtract it from my capacitive reactance. Remember, they're opposites, so they cancel each other out. 47.9 minus 14.3 gives me total reactance for my circuit of 33.6 ohms. Once I have that done, I'm going to go ahead and find my Z values. The first Z value I'm going to look for is my coil. I'm going to use Pythagoras theorem here. 47.9 squared plus 3 squared, and then if I square root that answer, I get 48 ohms of impedance for my total coil. For my circuit total, I use Pythagoras theorem again to get 33.6 squared plus 9 squared for total impedance on my circuit of 34.8 ohms. Remember that the total impedance of the coil has nothing to do with the total impedance of the circuit. I need to make sure I'm using my horizontal and my vertical values in order to figure that out. The reason why they're not associated is because they're at different angles, so I cannot use one directly on the other. Now that I have my impedance triangle done for my total circuit, my next step is going to be to calculate my current. I'm going to take my source voltage of 120 volts and divide it by my total impedance for my entire circuit of 34.8 ohms. I'm going to use Ohm's law and I get a value of 3.448 amps. Remember, since this is series, that amperage goes through everything, so that amperage is going to apply for the rest of the formulas that we're going to use. Now that I have my amperage, my next step is going to be figuring out my voltage drops. Remember, if I have this circuit physically in front of me, I can read the voltage across each one of my components. So I want my math to be able to predict what I'm going to read on my meter. In order to find the value of voltage for any one of my components, I need to take my current, which is my constant, and multiply it by the value of that component. For example, my resistor. I have 6 ohms of resistance. I want to take my current, multiply it by that resistance. Same thing with my Z of my coil and my X of my capacitor. When I do all my resistances, my VR equals I times R. I can do that for my resistor to get 20.7 volts. I can do that for the resistance portion of my coil to get 10.3 volts. Remember, I can't really measure that directly, but it's good to be able to calculate that because I can use that to prove values later. And then for my total circuit, I can either use the R value there, or I can also just add up these two to get a total value of 31 volts for my resistive portion. The next thing I'm going to work on is my reactive portion. My reactive portion is going to be Vx is equal to I times X. So it's my X value for both my coil, my capacitor, and my total circuit. When I use this formula, my coil is going to have a reactive voltage of 165.2 volts. Remember, this is my counter EMF portion that I'm going to be creating with my inductor. For my capacitor, it's going to build up a charge of 49.3 volts, which gives me a total reactive voltage of a 115.9 for my total circuit. Remember, my capacitor is offsetting my coil voltage. Lastly, I'm going to want to figure out what my actual voltage for my Z values are going to be. For that, I'm going to use Vz is equal to I times Z. I'm going to use that for the coil, and that gives me 165.5 volts across my coil. Now that's the number I can read on my meter. For my total circuit, it should end up that if I take the Z multiplied by the I should get 120 because that's how I found the I in the first place, right? So making sure that everything still works out in that value. Now I solved for all the different voltages throughout my entire circuit, and I can double check each and every single different component. So my next step is going to be figuring out the power of my circuit. First formula I'm going to use is to figure out for true power, which is going to be P is equal to I squared times R. Now, you have to remember that you want to use current as much as you possibly can because this is a value that's consistent. And if I've made a mistake somewhere, I don't want to compound that mistake by using an incorrect number. So always refer back to current as many times as you can. I'm going to take all my components and everything that has a resistance. I'm going to use my P is equal to I squared times R formula, and I can find the true power of all my components. For my resistor, it's going to be 71.3 watts. For my coil, it's going to be 35.7 watts. And for my total circuit, it's going to be 107 watts. My next thing is to find out my reactive power. My reactive power formula is Q is equal to I squared times X. So anything that has an X value, such as my XL or my XC, I'm going to be able to use this formula for it. Once I calculate it all out, my coil has a reactive power of 569.5 bars, my capacitor has a reactive power of 170 bars, and my total circuit reactive power is 399.5. Remember, once again, just as I did for the impedance triangles as well as for the voltages, my coil and my capacitors offset each other. So that's a minus formula there. The next thing I want to do is find my apparent power. Now this formula, S is equal to I squared times Z, I'm only going to use for the coil. I'm going to use a different formula for my circuit total, and I'll tell you why in a minute. So if I use this formula for the coil, I find that my coil has a total apparent power of 570.7 VA. As for my total circuit, I do want to use this formula here instead, S equals E times I. The reason for that is that my I is my constant value, so like I said before, I want to use I as much as I possibly can, but I've also been given the value of 120. So even if I made a mistake calculating out what my Z is, I can still use this to make sure that I'm correct. Always use the most reliable numbers if you can. My total VA for my circuit is 413.8 VA. You'll notice that my total VA is significantly less than my coil VA, and this is the advantage we have with capacitors. Because of that offset, I'm actually going to be pulling less power from the system, and that is to our advantage. The last thing I'm going to do is figure out my power factor and my power factor angle. Now I could have done this step at any point in time before here. Since I had my impedance triangles done, I could have found my power factor and my angle there, or I could have done the same thing when I calculated my voltages, or I could do the same thing when I do my power. It all depends on what you want to do as far as when you want to do this. To calculate what my power factor is simply my horizontal divided by my hypotenuse, or my watts divided by my VA, or my resistance divided by my impedance, whatever formula you want to use. It's the horizontal divided by the hypotenuse. So for my coil, I get a power factor of 0.06, which translates into an 86-degree leg. And for my circuit total, I have a power factor of 0.26, which gives me a 75-degree leg, which tells me that my capacitor has offset that value of approximately 11 degrees. Now my circuit is complete. I know all the values for it. I know what my voltages across each different component should be reading. I know what the power across each different component should be reading. I know all my circuit totals, and I can do whatever I want with this information to make sure that the circuit that I've built is actually performing the way it should. Okay, if you understand how we broke down that last circuit, then by all means, let's look at the next one. Here we have the exact same type of circuit. The only thing we've changed is the inductance and the capacitance. The resistance is still the same, the source is still the same. So pause the video now, solve this circuit the same way we solved the last one. Once you're done working on this circuit, resume the video, and then we'll step through it once again. Welcome back. Let's check to see how you did with this circuit. Whenever I do these circuits, I always want to follow the same type of pattern because it makes it easier for me to remember my steps and also to double check to make sure I didn't miss anything. So I always want to start with my impedance triangles, then I do my current, and then I'll do my voltage, and then my power, and then lastly I do my power factor and my phase angle. So let's get started with our impedance diagrams. When it comes to the impedance diagrams, I follow the same pattern. First thing I want to do is put down all my known values. Now I always want to follow the same lines. So first I'll do all my resistances. With a 6 ohm resistor, 3 ohms resistance inside the coil, I know that my circuit total will have a total of 9 ohms of resistance. After that, I want to take my inductance and my capacitance and convert them into my reactances. Using my formulas, I get 16.96 ohms of reactance in my coil. I get 10.87 ohms of reactance in my capacitor. And since these two are offsetting each other, my total circuit is 6.09 ohms of reactance. After that, my next step is going to be to find the total impedance of both my coil and my circuit total. My coil has a total impedance of 17.22 ohms, and my total circuit is going to have an impedance of 10.87 ohms. Now that I've found my total circuit impedance, and since I have my total circuit voltage, I can find out what my amperage is. Using Ohm's law, 120 volts divided by 10.87, I get a total circuit amperage of 11.04 amps, which is what I'm going to use for the rest of the circuit. I'm going to rearrange my page a little bit, and I'm going to show you a cleaner and simpler way to figure this out. And as you get better with these circuits, you find that you need to draw less triangles and do less stuff. As long as you keep yourself organized, you're going to be able to solve these things quickly and easily and spot any mistakes you might make along the way. Organization is key. So I've rearranged all my triangles. I've gotten rid of my picture because I don't really need it. I made sure I had my total voltage and my total amperage put out there. With everything I have on the page right now, I can solve the rest of it without even looking at anything else. Let's look at our voltages next. We do our resistive voltages. We get the 66.24 for my resistor, 33.12 volts for my coil, and you'll notice that since my coil resistance is half my resistor resistance, my voltages should follow suit, right? So my total voltage for my resistive portion is 99.36. The next thing I'm going to do is figure out my reactive voltages. The reactive voltage for the coil is 187.24. The reactive voltage for my capacitor is 120 volts. Therefore, the reactive voltage for my total circuit is the difference between those two being 67.24 volts. Remember, always offset. That's the biggest mistake people make, is they forget to offset those two, which is why I repeat this so very often in all my lectures. After I have all those voltages done, I'm going to figure out my VZ for my coil. Remember, this is the measurable amount I can use across the coil. Put your meter across there, you should read 190.11 volts. I don't need to worry about VZ for my total circuit because I already have that. That's E, that's my source. So I'm not going to worry about that. Once I have all my voltages done, I can move on to figuring out my power. Now the power, once again, I can use everything I have on here. I'm going to use my current. It's my I squared R, my I squared X, and my I squared Z formulas. First, once again, keep things as a simple pattern. Figure out your power first. The power for each of my components, my resistor is 731.29 watts. My coil is 356.64 watts, which means my total circuit power is the addition of those two, or my I square R on that gives me 1096.93 watts. You should always double check your numbers. So make sure that the other two powers add up to that one if you use the I square R formulas. Or if you use the addition, double check it with the I square R formulas. There's always a way to double check your numbers, and you should make it a habit to make sure you're going through your calculations. The next thing is my reactive powers. Resistor doesn't have any, so we can ignore that. We can calculate the reactive power of my coil and my capacitor, and once again, these two numbers offset each other to get my total reactive power. So with my coil being 2067.11, my capacitor being 1324.85, the difference between the two is 742.26 bars. If I was to draw a triangle here, it should be reflecting the triangles of my impedance. The last thing to do is get my total apparent power for all my devices. My coil, since it has more than one component, that gives me an S value of 2098.8, as well as my total circuit value is going to be 1324.8. So remember last time, I use the S is equal to E times I formula. And I'll do the same thing here. So 120 volts times 11.04 should give me 1324.8. I can also use the I squared times Z formula to double check that value. Once again, double checking is a very important thing to do. For my coil, I could have taken the 190.11 and multiplied it by my I, and that should have given me my 2098.8 as well. So double check, double check, double check. So far we have all of our values. We can measure a lot of these values, such as our resistances across our components. We can use a watt meter to read all of our wattages and all of our different power values. So the last thing we need to do is figure out our power factor and our operating angle. Our power factor and an operating angle for both these things should be different. I should always have a smaller power factor and a larger operating angle on my coil, and the inverse for my total circuit. Remember that capacitor is correcting our power factor here. So for my coil, I have a power factor of 0.17, sorry. That gives me an angle of 79.97 degrees. So we're almost at 90 degrees. However, for my total circuit, my capacitor has been able to bring that down significantly. So now my power factor is 0.82, and my operating angle for my total circuit is 34.11. If you really want to know, remember that the resistor has an operating angle of 0 degrees, power factor 1. Capacitor has an operating angle of negative 90 degrees, power factor of 0. So that's it. We've solved this circuit. How'd you do? Did you get everything right? If you didn't, go back through it and see where my calculations came up and where they're different from yours. And make sure you're really understanding the concepts that we're talking about here. You're going to be asked a lot of these questions when it comes to the AIT exam, so we want to make sure that you have a solid foundation in this. All right, you've reached the end of 202C, so you can now return to Blackboard. I do have a worksheet there waiting for you. You can do your knowledge check, and after you're done all of that, you can do a review of all three of these modules, both 202A, B, and C. Once you've done that review, you can go ahead and write your next test, which is S2-1.